This is a question on Young Modulus and Hooke's Law, January 07, and it previously was an A2 Module 4 question. It's now on AS1. So it's January 07, question 1. Some ballpoint pens have a spring in the barrel which is compressed when the user pushes the button at the end of the pen. Figure 1.1 shows a way in which the compression force depends on compression for the spring inside such a pen. The spring has an original length of 20 millimeters. Use figure 1.1 to determine the spring constant of the spring inside the pen. Right, so you have force and you have compression, and you know that F is equal to Kx. And therefore we need a value for K, so that's the gradient of the graph. And the extension has to be in millimeters, or compression in this case. And so if we just go to this value here, then you've got... So from our graph there, that is 1.2, and it's divided by, that's 8, so 9.6 by 10 to the minus 3. Don't forget about the by 10 to the minus 3. And that comes out as 125 newtons per metre. The spring must be compressed to a length of 12 millimeters for the ball point tip to be extended. Show that the strain energy in the spring when it is compressed is 4 by 10 to the minus 3 joules. So if it has compressed to a length of 12 millimeters, then the compression, its original length was 20. So the compression is 8 millimeters. And therefore, if we use W equals a half Fx, which is our formula for calculating strain energy, it's a half times, and we're going to use values from your graph. No, we're going to look at 8 millimeters here from your graph has a value of 1 Newton. So that's whenever it's extended. So that's a compression of 8 millimeters. There's a force of 1 Newton acting on it. So that's what we're going to use. So it's 1 times 8 by 10 to the minus 3. And that gives you an answer of 4 by 10 to the minus 3 joules. The pen is held vertically on the desk with the spring compressed to a length of 12 millimeters. It is then released, and the pen of mass 8.4 grams rises to a height of 40 millimeters above the desk. Calculate the percentage efficiency of the energy conversion from strain potential energy to gravitational potential energy as the spring returns to its original length. So we know that the strain potential energy we've calculated from the last question is 4 by 10 to the minus 3 joules. We need to calculate the gravitational potential energy, which is of course mgh. So the mass of the pen is 8.4 grams, which is 10 to the minus 3. G is 9.81, and the height it goes to is 40 millimeters, and that's of course by 10 to the minus 3. So mgh is 3.3 by 10 to the minus 3 joules. So we're going to look at how efficient that was in converting strain energy into gravitational potential energy. And so the percentage efficiency is 3.3 by 10 to the minus 3 divided by 4 by 10 to the minus 3. And that gives an answer of 82.4%. The time taken for the pen to rise to a height of 40 millimeters is 0.12 seconds. Calculate the power generated by the spring when it lifts the pen to this height. So power is energy over time. And the energy from the pen is the strain energy that was stored, and that's the 4 by 10 to the minus 3. And the time it takes is 0.12 seconds. And that gives you 0.033 watts, or it's supposed to be in milliwatts, so that's 33 milliwatts. Okay, part C. This is about specific heat capacity, which I'm not just sure that you have done. I'll just tell you what it is anyway. Specific heat capacity is energy required by a mass of 1 kilogram to raise the temperature by 1 Kelvin. I don't think this will be on anymore, but I'll answer it for you anyway. Each time the spring is compressed and released, 10% of the strain energy stored in it is converted to heat energy in the spring. Calculate the number of times the spring must be compressed and released to cause the temperature of the spring to increase by 1 Kelvin. So the energy required to increase the temperature by 1 Kelvin is calculated using the equation mc delta theta. And m is the mass of the spring, which is 0.24 by 10 to the minus 3. The specific heat capacity of the spring is 450 and the temperature rises 1 Kelvin. And so the amount of energy required is 0.108 joules is required to raise the temperature by 1 K. But every time it's compressed and released, there is 4 by 10 to the minus 4 joules converted to heat. So that's the strain energy in the spring. And therefore, to calculate how many times it has to be compressed and released, you'll have to divide your 0.108, which is bigger than 4 by 10 to the minus 4. And that comes out as 270. So I would say you wouldn't have to do a question like this given you haven't done this before, but sometimes it doesn't do any harm to see an equation in case they give it to you and ask you to use it.